Welcome to section 5.2, diagonalization. Okay, bunch of computations of eigenvalues and eigenvectors in the diagonalization stuff. Question 5 from this section says, find the eigenvalues and the corresponding eigenvectors of matrix A is given here. Also find an invertible matrix C and a diagonal matrix D such that D equals C inverse AC. All right. Well, diagonal matrix D will have eigenvalues as its entries, and matrix C will have corresponding eigenvectors as its columns. There's lots of eigenvectors, lots of choices for C, a few choices for D. The eigenvalues can go in different orders. We'll be consistent. We've set up a little technique where we've listed eigenvalues in terms of their increasing from lesser to greater as they lie along the real line. And we've religiously avoided complex eigenvalues. Okay. They want eigenvalues. We need characteristic polynomial. The characteristic polynomial is determinant of A minus lambda I. We'll set that equal to 0 to find the eigenvalues. So we'll take matrix A. We're going to take a determinant. So little vertical bars to take determinant of. Negative 3 minus lambda. Remember, you subtract the lambdas down the diagonal of matrix A. We need to take the determinant of that. How bad is that? Like the first column because of the zeros. So we've been through worse. And let's see, I messed up over here and failed to subtract a lambda from the 3, 3 entry. Okay, now we're good. So we get negative 3 minus lambda, the 1, 1 entry, times the determinant of the associated minor matrix, 7 minus lambda, negative 6, and then 0, 1 minus lambda for the rows, minus 0 times something, plus 0 times something, going down the first column, emphasizing the positive, negative, positive thing still, because it matters. Okay, and then I don't care, I'm taking advantage of the zeros. I don't need those other little minor things. And then we get negative 3 minus lambda times, let's see, 7 minus lambda times 1 minus lambda, going down the diagonal, minus, careful with the parentheses, negative 6 times 0, going down the back diagonal, but that 0 is helpful there. And so we get negative 3 minus lambda times 7 minus lambda, 1 minus lambda, and there's your characteristic polynomial P of lambda. So we'll set that equal to 0 to find the eigenvalues, and they will be negative 3, 7, and 1. We'll list them in increasing order. And then we'll have to go through and find corresponding eigenvectors. Let me hang on to the space over there. We'll compute, maybe compute one of these in detail, and the other two are over there hidden for now. So I got to reuse my space here. All right, so there's the characteristic polynomial. Set the characteristic polynomial, set P of lambda equal to 0 to get the eigenvalues lambda 1 equals, let's see, negative 3 would be the least, lambda 2 equals 1 would be next, and lambda 3 equals 7. Okay, now I've already made some decisions on how to index these. That's going to affect what the diagonal matrix D looks like at some level. Of course, I can list these in any order I want. At this stage, I'm free to do any of the possible orderings of those three eigenvalues, but that's going to imply some constraints when we start choosing the columns of matrix A. I need a correspondence between the columns of A and the diagonal entries of matrix D. What the hell? I can tell you what matrix D is already. So we'll take matrix D to be lambda 1, lambda 2, lambda 3 along the diagonals and zeros elsewhere. So we've got matrix D to be negative 3, 1, and 7 as diagonal entries. They wanted, they wanted eigenvalues. There's your eigenvalues. Put it in a box. They wanted matrix D, and there's your matrix D. Now we put it off as long as we can. Now we need corresponding eigenvectors for each of those three eigenvalues. All right, check my script and make sure my numbers are okay. Numbers are good. All right, so now, with some regret, for eigenvectors. Okay, let's do one of them in detail and we'll just pull the others up. Now for eigenvectors, we consider the system of equations, the homogeneous system of equations, A minus lambda I times vector V equals a zero vector. Okay, come straight from the definition of eigenvalue and eigenvector. So we're looking for non-zero vectors V that satisfy this. So we consider the associated augmented matrix, A minus lambda I. Oh, let's write it out symbolically maybe. We're taking A minus lambda I, augmented with zeros, coefficient matrix, augmented with the right-hand side. Sure, the zeros never change, but I'm going to keep up with them because it's what we're familiar with. A minus lambda I. Uh-oh, matrix A is gone. Here's a copy of it right here. So we get negative 3 minus lambda. See, we're doing this for, we'll have to do it for lambda. Let's say lambda 1. Let's go ahead and deal with lambda 1. So we consider things of this form. So when we take lambda 1, we'll get something of this sort. And let's go ahead and plug the lambda 1 in. That was negative 3, wasn't it? Yeah, negative 3. Second column would be 10, 7 minus negative 3, 0, negative 6, and 1 minus negative 3. And I need to augment that with zeros, not that there's much information there. Okay? So we need to solve that system of equations. All right, double check my numbers, and we're still good. Okay, simplify first. Negative 3 minus negative 3. Looks like that first column is zeros. Well, that's good news, ain't it? I better have a pivot-free column. We do already. Let's see, 7 minus negative 3 is 10. 0, negative 6, negative 6. 1 minus negative 3 is 4. Still augmented with the zeros. Okay. So let's do our reduction thing. Of course, I'm liking these two rows. Maybe treat this as a pivot. Want it to be 1 sooner or later. Let's make it later. I'd get fractions if I made it 1 right now. I may get fractions anyhow. We'll see. So let's take the 10 here and eliminate the 10 in that second row by taking row 2 and subtracting row 1 from it. Okay, so row 1 won't change. Row 3 won't change either. And we'll have, let's see, 10 minus 10 is 0. Negative 6 minus negative 6 is 0. Excellent. All right. Let's see. Yeah, I don't like fractions. Let's take, I've got some options here. Let's take row 3 and divide it by 4. Okay, so then row 1 doesn't change. Row 2 doesn't change. Row 3, the 4 becomes a 1. That's nice. Now let's use this 1 to eliminate that 6, and then we'll do the division by 10. So I've totally avoided fractions if I'll do it in this order. So we'll take row 1, goes to row 1 plus 6 times row 3. Okay, so I have limited board space here. And we're almost there. Then gives us, let's see, the second row doesn't change. I need to move that row to the bottom here pretty soon. Third row doesn't change. We're so adding 6 times this, so the only thing that will change is we'll pick up a 0 here. Let's take row 1, divide it by 10. Tell you what, let's take rows 2 and 3 and interchange them. A little careful with that, but it's all row 1 in this row operation, and it's all rows 2 and 3 in the other one. So we're good. Squish that a little closer together. So we'll have 0, 1, 0, augmented with a 0, 0, 0, 1, augmented with a 0, all zeros. And I was planning on at least one pivot-free column. We got exactly one pivot-free column. Good thing we don't have any pivot-free columns, and something's wrong. So we need to take that. Remember, we're solving for the components of some vector, v sub 1 we'll call it. So we'll convert that back into a system of equations. We've got v sub 2 equals 0. V sub 3 equals 0, and 0 equals 0. Or we want to write that as V1 equals, V2 equals, V3 equals. Okay, well V2 is 0, and V3 is 0, and I don't know anything about V1, so I'll write V1 equals V1, because that gives you no information about it. Right, because it's going to be a free variable. And we'll let R equals V1 be a free variable. All right, in terms of the system of equations, then we can rewrite V1 equals, V2 equals, and so forth as follows. V1 equals R, V2 equals 0, V3 equals 0. Here, R can be any real number. We've solved a system of equations. With the eigenvector stuff, there's a little extra nuance that you can't let the solution be the trivial solution. We can't use the 0 vector for an eigenvector. So, the eigenvectors of lambda 1 equals 3, negative 3, are of the form V equals, has components V1, V2, V3, and those components are any scalar R times, say, the vector 1, 0, 0. Pick off the scalar coefficients of R. There's one R here, 0 R's there, 0 R's there. Where R can be any real number. Oh, except 0. So there's the eigenvectors associated with lambda 1 equals negative 3. We need to do that 2 more times for the other 2 eigenvalues. Well, let's shortcut that. I got written up solutions for you that goes through all those details. But we'll find when we take lambda 2 equals to 1, similar type thing over here. Sadly, it's gone, erased. We'll subtract 1 along the diagonal. We've got our system of equations, blah, blah, blah. So I've buried a lot of stuff with that similarity tilde that's similar to this after some row operations. Again, see the written solutions for the details on that. We'll rewrite this as a system of equations. We'll move some things around. We'll introduce a free variable. Looks like it'll be free variable s equals v sub 3, third column. So we'll treat that as the free variable. And that produces apparently this for vector v sub 2. So eigenvectors associated with lambda 2 are of that form. If you'll consider lambda 3 equals 7, the setup's the same. There's a bunch of row reduction, and you'll be led to eigenvectors associated with lambda sub 3 of this particular form here. All right, so what were we doing? We were looking for eigenvalues. Got them. They were -3, 1, and 7. We were looking for corresponding eigenvectors. Got them. V, should subscript this one, v sub 1, eigenvectors associated with the first eigenvalue, eigenvectors associated with the second eigenvalue, and eigenvectors associated with the third eigenvalue. Now we got eigenvectors coming out of our ears. We've made matrix D with lambda 1, lambda 2, lambda 3 along the diagonal. So we need to make matrix C, and then we're done, with an eigenvector corresponding to lambda 1 as its first column, so we need to pick one of these. An eigenvector corresponding to lambda 2 as its second column, so we need to pick one of these, and we need to pick one of those for the third column. Okay, well, we've got infinitely many of each of these, so we need to pick a value of r, not 0. We need to pick a value of s. We need to pick a value of t, not 0. How about 1? And then we get nice little numbers for the eigenvectors. But we need specific eigenvectors at this stage. So the only thing we haven't done to answer their question is we haven't found matrix C. Okay, so we need specific eigenvectors. So let's take r equals to s equals to t. So I've used different letters for each of these to distinguish them. Let's take those all equal to 1 to get specific eigenvectors of the first eigenvector, r equals 1, and give us 1, 0, 0. Second eigenvector, we'll let s equal 1, gives us 1, 1, 1. Let t equal 1, 1, 1, 0. You want to use different values of r? I don't much suggest it, because these came out really nice with just 1s and 0s, but there's nothing to stop you. There's something to dissuade you. We're going to make a matrix out of these, and depending on the question, we might have to invert that matrix. Yeah, I'd rather invert a matrix that's a lot of 0s and 1s than a matrix that's got 7s and 15s in it. But there's nothing to stop you from setting s equal to 15 and taking the eigenvector 15, 15, 15. You'd pay for it if you had to find C inverse. You don't have to find C inverse in this one. They didn't ask that, though it's a common thing to ask in these exercises. So, matrix C is, to choose matrix C, we took, using the notation from Fraleigh and Beauregard, the first column of matrix C is this vector v sub 1. They put the little dots above and below it to indicate it's a column vector. I don't think that's really a universal notation. We'll use it because our guys, Fraleigh and Beauregard, use it. So anyhow, we get first column is this first vector, 1, 0, 0. Second column, 1, 1, 1. Third column, 1, 1, 0. There's your matrix C. We had matrix D above. We found all the eigenvalues. We found all the eigenvectors. Now, in matrix D, I've answered their question. Remember, we had matrix D was lambda 1, lambda 2, lambda 3 with zeros all over the place. We had, what was it, negative 3, 1, 7 along the diagonal. Now I said you can take those eigenvectors in any, so those eigenvalues in any order you want. You don't put the 1 here and the negative 3 there, you go right ahead. But that changes some other stuff. So if I'm taking 1 as the first eigenvalue, then I need to run up here and find a corresponding eigenvector. So if I put the 1 here and the negative 3 there, if I swap those two diagonal entries around, I'd have to swap these two columns around in matrix C. These are in corresponding positions. Column 1 contains lambda 1 in D. Column 1 in C contains an eigenvector of lambda 1. You put these things in a different order. You put these columns into matrix C in a different order as well. The order doesn't matter, but you have to do consistent ordering between the diagonal entries and the rows of matrix C.